Now that we've defined our thin lenses of converging and diverging types, we want to look at a geometric approach to locating the image produced by an object. But first, let's define our diagram pieces. There will always be an optic axis. I'll refer to that as capital X, horizontal axis here. The lens itself we'll label as L. Often a vertical line should give you the exact position of the lens along your axis. The lens needs to be oriented perpendicular to that axis for all of our work in this course. The object itself, we'll call capital O, is sitting here on the left of the lens. The lens has a focal length, which is lowercase f. This is the variable we use to denote focal length. If focal length is a positive number, that represents a converging lens, as shown here. And its primary focal point will be on the right side of the lens. We'll call that primary focal point capital F. There will be a secondary focal point, F prime, on the left side of the lens at the same distance away from the center of the lens. So it's a mirror image, secondary focal point on the left, primary on the right. If our lens has a negative focal length, we call that a diverging lens. As we discussed in the previous video, you will flip the locations of the primary and the secondary focal points. Now, let's come to this problem without the red rays traced, and we would say, I want to know how this lens maps the light from our object into an image on the other side. We consider only one point on the object which is emanating light. Of course, the entire object either produces its own light or reflects light in all directions, but we only need to consider one point here at the tip of the arrow, which is often the symbol that we use to define our object. And we will draw three principal light rays in order to locate the image location. The first, I've asked my students to name these over the years. The first we call the burning tinder light ray, which passes from your object parallel to the optic axis, bends at the center of the lens L, and passes through the primary focal point, like so. So this was labeled light ray 1. Light ray 2, you might think of as the mirror image of that one. You send a light ray from the object through the secondary focal point, F prime, on this side. It bends at the center of the lens L, and it emerges parallel to the optic axis. So that light ray is labeled 2 here, what we call the lighthouse. Right? Burning tinder is what you do with the parallel light rays coming in from the sun. You focus them down to a point where you want to set something on fire. With a lighthouse, you want to do the opposite effect. You want a relatively small source of light here to be projected out as far across the surface of the water as you can. So you want parallel light rays to emerge from the lighthouse lenses. The third is this ancient internet meme coming back to haunt you. It is the honey badger. My students named this because the honey badger doesn't care that the lens is in the way of the light. So you pass your light ray from the object along a straight line through the center of the lens at the optic axis without bending. So you just draw one continuous straight line through the center so that it passes across the axis at the center of the lens. Now you can see that third ray confirms our intersection point. Of course, any two of these principal rays will intersect at the location of the image. However, you draw all three of them to make sure that you haven't messed up the process. If you draw all three and you don't find a good intersection, then you need to go back and rethink your strategy. This image that is formed here, this is a case where the object distance to the lens, we call that object distance S, is greater than the focal length. And we have a focal length which is positive. The image that is formed, we call that image real, sitting here. If you were to place a screen at the location of the image, you put a white sheet of paper here, perhaps, and then you look, you observe that sheet of paper, you're going to see a focused image of the object on that screen. This indicates you have a real image. There will be three other examples, three combinations of focal length and object distance, which will give us something called a virtual image. And a virtual image will not form an image if you were to place a screen at the image plane. You will not see anything on that screen. What is required is to have another converging lens farther along the optic axis to project down, either to see an image projected onto a screen, or say the converging lens in your eye to project an image down onto your retina. So there are four possibilities. You can imagine focal length is positive, or focal length is negative. These are converging lenses. These are diverging. Then this item, which will be defined in the next video, what we call the object distance, S, because the letter S appears in the word object. The object distance can either be greater than the focal length or less than the focal length. You see there are four basic categories of images here. We've just looked at the case where the focal length is positive, it's a converging lens, and you place the object at a object distance S bigger than the focal length, you got a real image. That's this quadrant. But now what happens if we take the same converging lens and put the object, O, closer to the lens than the focal length? Well, the three principal rays are interesting now. The first one, recall burning tinder. You have to send out away from the object parallel to the axis, bend at the center of the lens, and pass through the primary focal point. So it ends up out here. The second, lighthouse, is supposed to pass through the secondary focal point on its way to the lens, but obviously it can't do that if you place the object closer to the lens than the focal point. So you put some dashed lines back here and set your ruler to connect that secondary focal point to the tip of the object. So you do some dashed lines telling you there's not actually any light back here. The light starts at the object, goes towards the lens, hits the center, and emerges parallel to that optic axis. The third is the easiest, always. Honey badger doesn't care. Starts at the object, passes right through the center of the lens, out in this direction. Now you can see this is a converging lens, but our light rays are diverging on the opposite side. What we must do is imagine ourselves again to be an observer over here. And that observer can use the lens in their eye to collect these diverging light rays, and they will see a virtual image, which is back here. How do we know it's there? Because all three of these light rays appear as though they're emanating from the same point. Extend your dashed lines back from the direction that the light rays are emerging from the lens with. Extend it back here, extend it back there, and extend it back here. You can see they all appear to come from the same location, and that is the hallmark of a virtual image. So in that situation with the converging lens, with the object distance smaller than the focal length, you get a virtual image. In the thin lens equation video, we'll define lateral magnification, which is this negative image distance. Image distance is S prime in these diagrams, divided by the object distance S. In this situation, you get an upright image because your magnification M will be positive. In this situation, you will also see that the height of the image, Y prime, is greater than the height of the object, Y. Those are the first two cases covering the converging lens. The other two cases, right, we could have a diverging lens where the object is placed farther away from the lens than the focal length. Okay, that looks like the following diagram. Again, you're following the same three rules. Always, if your rule tells you to pass through a focal point, and you can't, given that the light needs to travel left to right, you'll extend the line through that focal point with a dashed line. To remind you, the light is not actually passing through there. In this case, burning tinder, parallel, is supposed to go through the primary focal point, but that's on the wrong side of the lens. So it will emerge in a diverging sense this way, such that it appears to come from that primary focal point. The lighthouse is supposed to travel through the secondary focal point. So you start out with the light moving towards it, but then it will bend at the lens and emerge parallel to the axis. And always the easiest is honey badger, which goes straight through. And you can see now that the actual light ray 3 plus 1 and 2 appear to emanate from the same location here, and this observer would see a virtual image on the left side of the lens. It's upright because the magnification is positive. In this case, the image is shorter than the object, so the Y prime here will be less than Y over here. And finally, okay, so that was the case diverging lens object distance greater than f, we got a virtual image. In the final case, right, diverging lens, where we place the object closer than the focal length, you'll follow a similar ray construction and obtain a very similar result. Here you can see the virtual image to the left of the lens. The ray diagrams are very similar. And you can fill out the remainder of that four-part table with your diverging lens and object distance smaller than focal length. You still get a virtual image. The only way to obtain a real image is with a converging lens where the object is farther out than the focal length. So we can take these three principal rays, the final video of this series, and derive the thin lens equation, which we will apply in class.